I hope you all had a good break. Anybody got any stories to share? Nope. All right. It's what I expected. I hope you had a nice time. We are going to have our big test this week on Friday. So that's instead of our usual class. You should expect the test to be kind of like our quizzes, but like bigger, and it'll take up the whole class time. I hope that everybody has been following along with your quiz grades so far. You will want to know which of the questions you have full credit on. I hope everybody understands the system. So the test on Friday will have one of every question, but the ones which you've already got full credit on, you don't have to do them. The ones that you do are, this is just an opportunity to raise your score up on the ones that you've already done. Yeah?
Are the questions like marked which topic it is?
Yeah, they're going to be sort of, 1, 2, 3, like the numbers on the questions correspond exactly to the numbers on the big checklist. So during the test, you should bring your big checklist with you, just so that you can remember which ones you want to do. Although if you can remember it yourself, that's fine too. And different people among you will have different ones that you want to do. Some people will be trying to do all of them. Some people will have just a few to do. So don't be alarmed if somebody leaves right away or if somebody doesn't leave right away. Yeah. No, if you have full credit on everything, then yeah, there's no point in. You could show up and just like immediately hand me the blank thing as a flex and then walk out. But I think that this will at least include a question about improper integrals, which has not been on any of our quizzes. So everybody will at least want to do at least that one and maybe one other one. I'll have to look at the list. So I don't. Certainly, I mean, if there's only one question, like you don't have to do it if you really love skipping tests. There will be at least one question that nobody already has credit for. All right. Any other questions? Please let me know if you've like somehow lost track of your checklist. I mean, you can, if you want, you can print out another one. They're on the class website where the homeworks are. But if anybody's unclear on the system, I know it's a little confusing, but it's not too confusing, I hope. All right, great. Let's just talk some more about improper integrals. That's what we were doing before the break, and then tomorrow. Ordinarily I like to do sort of like a time of review before the exam, but I think, because everybody's going to be doing totally different things on the exam, I'm not sure that it's worthwhile to do that sort of thing. But I would be happy to, as usual, get together with anybody who wants to go over things for the test. I would be happy to do that. A little announcement. I don't know if anybody cares, but tomorrow morning I have sort of a non-standard meeting at 11 a.m., which is usually a time that I'm sitting in my office talking about homework. So tomorrow, our class is 9 to 10. I will be free 10 to 11, but not 11 to 12, in case anybody was planning on that. Let me know if that's a problem. I hope not. So I think I was saying I don't think it makes sense to do like a bunch of review time during class, but I would be happy to get together with anybody and chat about things. So we will just do like new stuff today and tomorrow. And I think, usually people ask me like, is this new stuff we're doing going to be on the test? And usually my answer is no, like I'll give you some time before I put it on the test. But I think given the format that we're doing, I might as well just put the stuff on the test. And even if you haven't had a lot of time to sit with it, you might get lucky and get it right, and then you won't have to deal with it in the future. And if not, then by all means, don't stress out about it. Right? So the test will include everything, even the new stuff that we're doing today and tomorrow. You may see on the test. If you don't like that, just don't do it. It's fine. All right. Great. Let's talk some more about improper integrals then. Just to refresh your memory, I'll do a sort of a very standard one, and then there are some types of improper integrals that we never got to. So like some kinds of things to consider. Remember, the basic idea of the improper integrals is that it's an integral where one of the boundary values is going out to infinity. So, the classic, the thickness. The classic example is something like that, right? And this represents the area under the curve of 1 over x, which is this function, from 1 to infinity. That's this area here, right? This is 1 over x. And it's the area from 1 up to infinity. Now that area stretches on forever to the right, but it's not clear if that area actually is infinity, or if, even though it stretches on forever, we've seen in examples, it is possible that you can have an area that stretches on forever, but even so does not actually add up to an infinite area. Now this example we did last time, this area really is infinite, although sometimes they are not. And the way that you would figure that out is you immediately change this into a limit as t goes to infinity, integral 1 to t, 1 over x dx. So this is always the first step when you are trying to actually work out the value of one of these improper integrals. You replace the infinity by a variable, and then you do this integral on the inside of the limit. I do the integral. So sort of ignoring the lim part until the very end. We do the integral. Integral of 1 over x is ln x, ln of absolute value of x, I guess. And then I'm going to plug in 1 and t. We plug those in. It says lim t goes to infinity, ln of t minus ln of 1, right? These are, the absolute value doesn't matter because these things are both, of course, 1, absolute value of 1 is 1, and t is positive, so absolute value t is the same as t. All right, ln of 1 is 0, and ln of t, so this part, ln 1 just straight up is 0. And then the other part, we have to think about the limit, the lim of ln of t. But just because we know something about the graph of ln of t, when the graph of ln just kind of like goes up and to the right as a curve, it goes up forever though. This actually is infinity. You could say equals infinity, or you could say does not exist, or undefined, or something like that. The terminology that we usually use in the context of these improper integrals is the integral, we say, diverges. That means that this area that we're talking about does not actually settle down on any particular number. It just continues to increase forever, that area there. The integral diverges. All right. And that's why I said at the very top there, this area really is infinite. All right. This was a very simple one just to refresh our memory. Any questions about that? This is the very basic kind of improper integral. All right. Sometimes you get a real number answer at the end, and then you say the integral converges to that number. I thought, just for fun, how about a here's a fun one. They're all fun ones, aren't they? How about, this is fun because it's a bit of a blast from the past. Some of you may want to review this before we do the test. How about this? What if I take the same thing, 1 over x, but instead of the area under the curve, let's make a solid of revolution out of it. This kind of like infinite sort of, bugle shape, right? So this volume of an infinitely long, I'll call it an infinite bugle, all right? Now, it may be that the volume of that actually is infinity, or it may be that the volume of that, just sort of equals some specific number, all right? We have to work it out. It'd be a little weird, in my opinion, if the volume was finite, because we've already seen like the area, that area, if you just made it flat, that area would be infinity because of this, right? We just said that's this area. That's half of it, but half of infinity is still infinity, all right? So the area in there would be infinite, but what about the volume? So how would we work this out? I hope we, at least I hope a lot of you remember the volume of revolution formula. That's what I'm going to be using here, where I'm going to do it this way, this kind of washers method. You slice it up. This is an easy one of those because the slices just look like ordinary circles. And so, you know, this was the thing about the inner radius and the outer radius, that business. But actually in this case, there's no inner, it's all, the slices are just straight up circles. So the formula that we're going to be using is this one. This, right? If you do have the inner and the outer, this formula would say pi on the outside and then the outer radius squared minus the inner radius squared, right? But in this case, we don't have any kind of holes in the center of these cross sections. They're all just plain circles, and so we can just use this basic formula. Now the boundaries on the integral, they should go, I'm intending to start at 1 there and then go out to the right forever. So the boundary should go 1 to infinity, all right? And then my function, f of x, of course, is 1 over x in this example. So we should be able to just plug everything in and do it as an improper integral. So this is going to say pi, and then the integral I turn into a lim. T goes to infinity, integral 1 to t. And then f of x is 1 over x. We square it. It looks now like 1 over x squared. All right. And then we will work this out. The answer either will be some number or, you know, does not exist or something. Anybody have a suggestion? How do we handle the integral of 1 over x squared? I'm going to do the antiderivative of that. Yeah. Write it as x to the negative 2. Yeah, great. So I got my pi here. Happy Pi Day, by the way. I hope that you all celebrated responsibly. I actually didn't eat a pie. Did any of you eat a pie for Pi Day? Come on, killing me. What's happening to our country? All right. Yeah, so that's how you handle 1 over x squared. You write it as x to the minus 2, and then when I do the antiderivative, we do the thing with the exponent. Minus 2 increases by 1 and becomes a minus 1. So this is pi on the outside. Lim t goes to infinity. I just end up with minus x to the minus 1, plugging in 1 and t. And we plug in. So that's a pi out there. It says minus t to the minus 1 minus it's a plus 1 to the minus 1, right? And now you have to actually do the limit, and you ask yourself, what happens to t to the minus 1? I don't know if you like t to the minus 1. I find this a little easier to think about if I write it as a fraction again. This would be negative 1 over t plus, I guess, just 1. And then can somebody say, what happens to 1 over t when t goes to infinity? You have to think, usually it's like either this thing becomes 0 or it becomes infinite and the whole answer does not exist. What do you think? Yeah?
It becomes 0.
It becomes 0, yeah. 1 over t, where t is becoming infinite. If you have something that's like infinity in the denominator, that becomes 0. So yeah, that part is just going to be 0 when we do the limit. And so my full answer is just pi 0 plus 1. So it's just pi. All right. So that means that this is actually kind of counterintuitive and very strange in my opinion. It means that infinite sort of bugle thing, it actually has a finite volume, and the volume equals pi. Even though the area of a similar shape, if you flatten this down, it has infinite area, but as a volume, it's finite. Very strange. Strange but true. What kind of sense does that make in real life? The answer is like, in real life we don't have infinite bugles, and so it doesn't really come up. But this is very weird. You know, infinity be weird. That's all I can say. Infinity be cray. Do people say that? I've heard people say cray in this way. Right? Infinity is a strange thing, but these are all weird things that can happen when you consider infinite bugles and such. All right. Anyway, I got a quick example for you all just to make sure everybody still knows what's up. How about the integral from 4 to infinity? See what you think about this guy. All right. I will remind us all of a integration formula that I hope you remember. You should make use of that when you have x inside the exponent. See what you think. I'll give you a few moments. All right, can we chat about this? I see some good progress out there. So the very first thing, and this is not something you have to give any thought to, you write this instead of infinity in the integration boundaries, you write it as a limit t goes to infinity, and then put the t there up there. 1 over 5 to the x, it is appropriate to rewrite that as 5 to the negative x. It's because I intend to use this rule over here, and I want this to look as much like that as possible, right? 1 over 5 to the x is a little inconvenient for the sake of using this formula over here, because I want it to be just 5 to some power, not 1 over 5 to some power. All right, anyway, that's just replacing the t and then rewriting 5 to the minus x. Now we can do the antiderivative. The lim will stay out here. We don't do the limit until the very end. X to the minus 5, antiderivative of that is 1 over minus 4, x to the minus 4. That's just an ordinary antiderivative of a power of x. And then 5 to the negative x, the antiderivative of that, I use this formula over here where a is 5, and instead of x, I have negative x. And the fact that there's a negative x instead of x means this whole antiderivative also picks up a minus sign. So it's going to be minus 1 over ln, 5 to the minus, 5 to the minus x. And then we plug in 4 and t, right? That's the antiderivative. I'm using that formula up in the corner there where a is 5, and instead of x, I have minus x. And because of that, we also need to negate the entire antiderivative. That's why there's a minus here and not a plus. It's because of the negative x instead of x. All right, now just to finish it off, we plug in the values t and 4. So this is, still got my lim here, plugging in t, 1 over minus 4, t to the minus 4, minus 1 over ln 5, 5 to the minus t. That was plugging in the t, and then we subtract and we plug in the 4. 1 over minus 4, 4 to the minus 4, minus 1 over ln 5, 5 to the minus 4, like that. All right? Now the stuff inside the parentheses there is just some number, which if you want you could plug into your calculator, but that's just going to be part of the answer. The other stuff with the t's in it, we have to take the limit as t goes to infinity. And so in order to do that, again, I find it easiest, I mean, maybe you can do this directly if you, which is not a problem if you like, but I find it easiest to write these negative exponents as fractions again, so that I can think about how do I do these limits. Writing them again as fractions, this will say 1 over t to the 4, and then minus 1 over ln 5. 5 to the minus t is the same as 1 over 5 to the t, right? And then minus this same stuff here. Those numbers are just going to stay like they are inside the parentheses, all right? To me, it's easier to see what happens when we do the limit if I write all these negative exponents as fractions again. And what does happen when I do the limit as t goes to infinity? I'm looking specifically at this guy and this guy, and I think both of them become 0 in the limit as t goes to infinity, because in both cases I have a fraction where the thing on the bottom is infinite, right? Here it's like something super big to the 4th power, which is super big, and here it's like 1 over 5 to a super big exponent, which is again a super big number. So in the limit, both of these parts become 0, which means my final answer is 0 minus 0 minus this number. So really this number at the end is the whole answer. It's like that. All right. Generally speaking, when you do these limits at the end, it's either going to be 0 or does not exist. And it depends on if that variable ends up in a denominator or in a numerator. If that variable, the t, is in a denominator, when you make it go to infinity, the thing becomes 0. And if it's in a numerator, then when you make it go to infinity, the thing stays infinity. All right. Anybody got questions about that one? I hope that this one worked out for you. Great. All right. I got two more 3 more examples. There are some variations. So this one here is somewhat complicated, but more or less a normal one of these. I wouldn't say an easy one per se, but it's fairly straightforward doing ordinary integrals and getting the answer at the end. There are some where you have to do extra tricks. So some fancier ones. The first way that these could be fancy is that sometimes you have to do tricks in order to do the integral, right? And so here's an example like that. How about 0 to infinity x e to the minus x squared dx, right? In this case, the thing inside there is a weird thing. You can't just do the antiderivative right away. We have to use one of our integration tricks. So this can happen sometimes when you're doing these improper integrals. Sometimes you have to use one of the tricks. The tricks being like the u substitution, the integration by parts, the partial fractions. Is that it? I think maybe those are all the tricks that we've talked about. Anybody want to suggest what's the appropriate trick that we should use in this case? I'll give you a hint. It's not the partial fractions. The partial fractions is used when you have a fraction with polynomials on the top and the bottom, which is not the case here. You got an idea? Is it integration by parts, he says. Anybody have another idea? Integration by parts is not a terrible idea because you do have like two things multiplied together, which is the classic situation for integration by parts. The problem is that second thing, which I underlined, is still fairly complicated. It's a square inside of an e, which is not gonna be very well behaved when you try to do integration by parts on it. Any other idea? Yeah? U substitution. Yeah, this is the only other idea that you could have. Can you tell me what I should use for the u?
Negative x squared.
Yeah, this one actually works out nicely with the u substitution. And you know, if you're presented with this one on a test, you're not going to know which technique to use. And my suggestion would be you can try to do the parts and see if it works. And in this example, it's not going to work. And so when you see something that's not working, you should go back and try something else. Yeah, she said, and I agree, u equal negative x squared. That means the du, I hope everyone remembers how to do the u substitution. The du is the derivative of the u, which is negative 2x dx. And then when I look at the thing that I'm integrating, I see right there is e to the u. And then the rest of it is x and dx, which I am encouraged by because I see x and dx here as part of the du. The way I would write this is divide the constant over there, so it's going to say 1 over, well, negative a half du equals x dx, right? Like so. So when I do the substitution, well, can I say, I didn't even do this, but you know, as usual, since I'm doing an improper integral, I change it into a limit. So this is the limit 0 to t like that. And then I go x times e to the, so just to write this u substitution out in a few steps, I have e to the u, and then what's left over is x and dx, all right? And then x times dx is the same as negative a half du. So would you mind if I factor the half out? Negative a half integral 0 to t e to the u du, right? Now here I did not change the integration values. You know, if you like, you can change the values, although it's weird to do that in a problem like this because the upper value is a variable, which is not very convenient usually. So I'm just going to leave it like it is and make sure to replace the original variable at the end before taking the limit. All right, what is the integral? E to the u du? It's just e to the u. So this becomes lim t goes to infinity minus a half e to the u. That's the antiderivative. And then I have to plug in the values 0 and t, but we don't plug them in for u. Remember, those are x values. So I should replace the original variable. T goes to infinity minus a half e to the negative x squared. Remember, that's what the u is. And this I plug in 0 and t. All right, plug them in. What do we got? 9 minus a half e to the minus t squared minus minus a half e to the 0, right? E to the minus 0 squared. E to the 0, of course, is 1. What happens to the other part? The lim as t goes to infinity. Again, I have a negative exponent here, so I would like to write that like a fraction. When you see a negative exponent, to me, if I'm trying to find these limits and I see a negative exponent, it's a lot clearer to me if I write it as a fraction. So I say 1 over e to the t squared, right? And then I guess that's plus a half, because e to the 0 is 0. E to the 0 is 1, so that becomes plus a half at the end. And then what happens when you do this limit? That little piece there, 1 over e to the t squared, you should be asking yourself, does this become 0 or does it become infinity? And the answer is it becomes 0 because the t, which is going to infinity, is in the denominator. So this again will look something like 1 over infinity, which is 0. So this is 0 when I do the limit. And so my whole final answer is just 0 plus a half. The answer is a half. Right. Sometimes those limits at the end can be a little tricky. I find it easier to see it all if I just write them as fractions. Any thoughts about that one? All right. Sometimes you got to do some integration tricks. I got one more of that type. How about this one? I know they like it out there. This one you should do with the parts. This is a classic integration by parts example. The only difference really is that the squaring up top. In the previous example, the squaring up top really makes it much more complicated, which makes it so that you have to do the u substitution. But in this case, we can just do parts. I should say my boundaries. Let's go 1 to infinity. All right. So this one, you should do parts. And it works out fairly similar to the previous one, although something interesting happens at the end, which is why I wanted to do this one also. Any expert integration by parts out there? What do you want to choose for the u and the dv? Any thoughts? Yeah. Yeah, let's take u as x, dv as e to the minus x. Remember, generally speaking, the u should be something that gets easier when you take its derivative. And in this case, u being x, when I take the derivative of that, it will go away entirely, which is great. So the du is just 1 dx. And then the v is the integral e to the minus x, which is minus e to the minus x. Sorry, I should put dx as part of the dv. Everybody knows that, right? This is a classic integration by parts type example, which will work out nicely. So when I do the integration by parts, let's turn this into a lim first of all. 1 to infinity, x e to the minus x. This, doing the integration by parts formula, becomes, I have to keep this lim out front, uv minus integral v du. Remember, that's the integration by parts formula. So I'm doing uv minus integral v du. That, in this example, looks like u is x, v is negative e to the minus x. That's the uv minus integral v, negative e to the minus x. Du is just dx. And remember how to do integration by parts with boundary values. You do the entire thing here. So I'm not done doing integrals because I still have this integral to do. But then at the very end, you plug in the two values to everything that you see here. So I'm going to continue doing that integral. The two minus signs will cancel and make a plus on the outside. And then we can just do the integral of e to the minus x is, again, negative e to the negative x. So doing that second part of the integral gives me, I'll write this one as minus x e to the negative x plus, well, it's plus another negative e to the negative x. And then we go plugging in 1 and t. sorry, I just realized this is a mostly unimportant typo. That infinity, I meant to say t. That's the first step is always to replace the infinity by a t. It doesn't make sense to put the reason you put the lim out here is so that you don't put the infinity on the inside. Sorry about that. Put a t there. All right, not quite done, but this is, we're almost done, right? The last step is to plug the values and then do the limit. So plug the values. Plug in t first. I got lim on the outside. Plug in t first. It says minus t e to the negative t. And then minus e to the negative t. And then subtract and plug in 1 everywhere. Minus 1 e to the minus 1. Minus e to the minus 1. Right? And so my answer, like this part is just whatever that is. This is some number that you can do on your calculator if you like. E to the minus 1 is, 1 over e, whatever that is. What about this business over here? We have to do the limit of this business over here. As usual, I'm going to write those negative exponents like fractions so that they look nicer to me. Although if you like, you can keep them the way they are. But t times e to the minus t. E to the minus t is the same as 1 over e to the t. So this guy looks like t over e to the t, right? And then the next one, minus just 1 over e to the t. And then, of course, we have this thing at the end, which I'm just going to leave like it is. Actually, those two parts are the same thing. Negative 2e to the minus 1. There, I will just simplify a little bit. It's like that. Those two guys just add up inside the parentheses, and then we have a minus and a minus. All right? And then finally, we just do the limit. And here is where something slightly interesting happens. I said something interesting was going to happen at the end. When we just do the limit, we have really two different limits that we need to think about. The second one is not terribly interesting. It just looks like 1 over infinity, which is going to become 0. Right? This sort of looks like 1 over infinity, which is 0. Right? What about the first one? This is what I said something interesting was going to happen. T over e to the t. When I take t to infinity, what I have on top is becoming infinity, and also what I have on bottom is becoming infinity. So this one, when I think about what would happen if I use t going to infinity, it kind of looks like infinity on the top and also on the bottom. Does anyone remember what that means? Is that like, does that mean 1? Because they cancel, or what? What do we think about that? It does not mean 1, because, as I always say, infinity be cray. You can't just cancel them out. Yeah. Yes, this is the situation when you have to do the L'Hopital's rule. When you see infinity or 0 over 0 or something like that, it means you need to do this limit using L'Hopital's rule. So when we see that, it means you have to do the L'Hopital's rule. Just for that piece, right? The other two pieces are fine. Like this piece in the middle is 0, and this, it just is what it is. That's just already a specific number. It's just that thing at the very beginning. We need to do the L'Hopital rule on that. So can I say, maybe just like as a little sidebar, and then we'll plug in. Really what I'm talking about is, what is this limit? T over e to the t, right? And this is what we need to use the L'Hopital rule on, because it's infinity on the top and the bottom. And this is actually an easy L'Hopital rule example. I hope everybody remembers. You take the derivative on the top and also take the derivative on the bottom. So derivative up top, and then you take the limit again. So derivative up top is 1. Derivative on the bottom, e to the t, becomes e to the t again. And then we, again, try to do this limit. What do we get when I do this limit? This time, it looks like 1 over infinity, which really is 0. So this limit is 0. All right. So this whole thing that I was making a big deal out of actually ends up being 0 anyway. But, of course, you have to work that out to make it so. All right, so my final answer then, like continuing from up here, this whole thing is just 0 minus 0 and then plus 2 e to the negative 1. So the answer is 2 e to the minus 1, or or 2 over e if you prefer. All right, the moral of the story is when you do that limit at the end, sometimes you got to use fancy limit tricks. And in this example, it was the L'Hopital's rule. All right. All right, great. One more thing about improper integrals. I hope you're not sick of this just yet. One more thing about improper integrals. And this, unfortunately, is kind of like the hardest of these variations that I've been talking about. There are also what I would like to call sneaky ones. This is an improper integral that actually, when you look at it, it doesn't even look like an improper integral at all. Here is a classic sneaky one. Now, if I just showed this to you, you wouldn't even think this is an improper integral at all because you don't see infinity here. And in fact, you could show this to your your little brother who is only taken Calc 1, and they would feel like they know how to do this. Don't write this down because this is actually wrong. I'm going to do this in red. Your idiot brother would do something like this. Just do ln x and then plug in 3 and -1. That's ln 3 minus ln, I guess here for once in your life the absolute values actually matter. ln 3 minus ln 1. Of course ln 1 is 0. Your stupid brother will be very satisfied that he knows that. And you get ln 3, all right? This is actually the wrong answer though. Can anybody see what the problem is? What would you say to your stupid brother? I shouldn't be so insulting of your brother. This is not actually, this is a sneaky one, right? Yeah?
The -1 isn't in the domain of the function.
It's something like that. Although it's not exactly what he said, -1 isn't in the domain. Actually, it is. Like you can plug -1 into this function, and there's no problem. But yeah, it's related to that. Anybody see a maybe variation on this observation? It does have to do with the domain of the function, though. It's not a problem with -1. What's the number which will mess this function up? Its domain?
0.
It would be 0. Yeah, this function, you will notice, you're not allowed to put 0 into this function. Is that a problem? The answer is actually yes. Like if you think about what this integral is supposed to represent, it's supposed to represent adding up the area, starting at -1 on the left, and then going up till you get to 3. And that process of going up to 3 goes through 0, which is a problem for this function. Like if you think about what this looks like on a picture, 1 over x looks like this, and I'm asking you to find the area from -1 up to 3. It's this area. And at this point you realize actually this kind of is an improper integral. Like this kind of is an integral where the area goes on forever. It's just not because you're going out to infinity, but it's because the integral is going through an asymptote of the function. Is that a question? No, you're just holding your fingers up. Ambiguous fingers. Yeah, this one here, so I will say this is integrating through an asymptote. And that is, I mean, to your stupid younger brother, I would just say you can't do that. It's not allowed, and you might feel like you get an answer at the end, but the answer you get is definitely not correct. Like this answer of ln 3, whatever that area, like to me, this area looks like infinity. It's definitely not ln of 3 though. So this is the wrong answer. And the reason that it's wrong is because when you're integrating through an asymptote, you could either just say like you can't do that, or at least you have to do something special to handle this situation, all right? What we do to handle this situation, you could just say you're not allowed to do that, but actually we do know how to handle situations when the integral involves these kinds of areas which seem to stretch out forever, and that is you turn it into a limit. So this is integrating through an asymptote. We handle this by using limits. Now, the limit that you're using is really as you approach 0, because 0 is the sort of point at which things get messed up in this particular example. And so we are going to first split the integral around the asymptote. What I mean by that is you make it -1 to 3, 1 over x. This instead I write as integral -1 to 0, 1 over x, plus integral 0 to 3, 1 over x. All right? Because really, I mean, you can see on the picture, really what we're talking about here are two separate regions. There's the one to the left of that asymptote and the one to the right of that asymptote. And really, we need to consider them separately. Split the integral around the asymptote, and then each of those two integrals we do as improper, where the limit is not going to infinity, but just going to 0. So 0 is the sort of improper point here. Maybe I'll say improper value, right? In all of our other examples, you just see an infinity there, and you know that's the one that you have to turn into a limit. But in this case, you have to somehow realize that the improper value that we're talking about in this example is 0. 0 is the improper value, so we make it a limit. And so what I'm going to do is lim t goes to 0, integral -1 to t, 1 over x dx, plus integral t to 3, 1 over x dx. And then we just do both of those integrals separately. It's a little bit of a pain to do the integrals separately, but they're both the same function, so you should just be able to, whatever steps you use to do the integral, it's going to look the same both times. Right. Actually, I'm going to split this up. I meant to write it this way. This is more or less the same, but sorry. Put the lim in front of each one, just so that you can do them two separate things, right? Individually, hopefully these integrals and limits will not be so difficult. And actually, in my opinion, these limits are a little easier because it's not a limit going to infinity, but just a limit going to a specific number, which I find a little bit easier to handle. Anyway, let's just do these separately. And then we're going to just add together the answers at the end. Or if either one does not exist, it just means the entire answer does not exist. All right? So let's try the one on the left first. It's going to say lim t goes to 0, integral -1 to t, 1 over x dx. What is the integral of 1 over x? The antiderivative is ln of x, as always. So this is going to become, I still have my lim here. Sorry, t going to 0. ln of t, plugging in -1 and t. What? ln of x, sorry. It can be confusing with the, I should say absolute value x. It can be confusing with the x and the t, but the x is the one that goes inside of the integral. The t is on the boundaries. All right, plug in the values. I say lim t goes to 0, ln absolute value t minus ln absolute value -1. ln absolute value -1 is the same as ln of 1, which is 0, so that part is no problem. It's the other thing that's more interesting. That thing at the end just equals 0. But here I have lim t goes to 0, natural log absolute value t. What is that? As t approaches 0, what happens to the natural log of t? Is this 0? Is it 1 maybe? Does not exist? This is a little strange, but when you're doing limits like this, basically you would want to just plug this value in here and see what you get, right? It would say ln of 0. What is ln of 0? Is that anything? Is it 1? Is it nothing? It's not 1. The thing about 1 is ln of 1 equals 0. But what about ln of 0? This is not something that we typically talk about. Remember, I hope you remember what the graph of the natural log looks like. It looks like, this is the graph of ln. It looks like this. 0 is actually a vertical asymptote for the natural log function. That means this limit here does not exist. If you like, you could say this limit equals negative infinity this is the graph of ln of t. And as t goes to 0, this graph just goes down forever. So this right here, you could say equals negative infinity, but in any case, I will just say this diverges. And that means the entire, remember this was only the first half of what we're doing, but actually if one or the other half diverges, then the whole thing automatically diverges. All right, so that was this part, minus 1 to 0, 1 over x dx. This diverges. So the whole thing, that was supposed to be one of 2 halves that we had to do. But if one of the halves is already infinite, then the whole thing diverges. So minus 1 to 3, 1 over x dx diverges. All right, that is how it goes. Anybody got thoughts about this? This is a tricky one. What's tricky about it, in my opinion, the trickiest part is just realizing that it is an improper integral at all, at the very beginning, right? You have to look at this and realize that there is a discontinuity of this function, a place where the function is undefined inside of the integration region, and so you have to turn it into an improper integral. All right. Any thoughts about that? I got a couple for you to try of these ones with variations, and then I think that'll probably do it for us today. How about you try these? The first one is a more ordinary one, although you're going to have to use one of your favorite integration tricks. See what you think. Actually, I'll give you a hint. Both of these you have to use the U substitution. so that you also have to think about splitting this up. Like where exactly you're gonna split it?
Oh yeah.
gotta go in a few minutes. Let's try these out. So as I was going around, pretty much everybody worked out the first one. Great. The first one, I'll sort of give the highlights here. Of course, you change it to t going to infinity, 0 to t. And then I'm going to do u substitution here. U equals x squared plus 1, so that the du is 2x dx. And then when you do the substitution, this should end up looking like 1 over u to the 4 times 1/2 du. I hope that's what you, this is what pretty much everybody said, I think. And then I'm going to pull the 1/2 out and then change 1 over u to the 4 to write it as u to the minus 4. So it's going to look like 1/2 here, integral u to the minus 4 du. And then we do the integral. T goes to infinity. Do the integral. I have 1/2 from before, and then negative 1/3 u to the minus 3. And then I'm going to replace the original variable, which was x squared. So this is lim t goes to infinity. I suppose negative 1 over 6, and then it'll say x squared plus 1 to the minus 3, and then we have to plug in 0 and t. I hope I'm doing all right so far. I'm doing this quick because pretty much everybody worked this one out. So what is this? When I do the limits, for the purpose of doing the limits, I find this easiest if I write them as fractions. So it's minus a sixth, and then negative 3 power is 1 over x squared plus 1 to the 3. I was going to plug them actually in. So this will be a t squared plus 1, and then subtract negative a 6, 1 over 0 squared plus 1 to the 3, like so. I think I'm doing all right. And then doing the limits, what do we get? So the second part of this answer is just whatever that number is. I think it's just negative, well, it's going to be positive because of those two. This is just 1/6 over here. And then this part here, when t goes to infinity, because t is in the denominator, that makes this fraction become 0. And so my final answer, the first part becomes 0, and the second part is just 1/6. So I get 1/6. Any questions about that one? I saw pretty much everybody got this, so I feel good about that. It's a bit of a journey to get there, but we get there. Okay, and the other one was integral 1 to 10, 1 over x minus 4 squared dx. All right, this one I also am going to do a u substitution, but there's another issue here, which is the business about splitting the integral. In this case, this function has an asymptote at x equals 4. So this is discontinuous at x equals 4. That's because 4 makes this denominator into 0, and that is not allowed. And so I need to, before we try anything, I need to split this up as the integral 1 to 4, 1 over this stuff, plus the integral 4 to 10. I think everybody settled on this eventually. And those 4s are the improper value, which I need to turn into a limit. So maybe I'll just focus on the first one first. We have to do each of them separately, but I'll just do the first one. Once you work the first one out, then the other one is done by the same methods or whatever. So I turn this into lim t goes to 4. 4 is the sort of problem value in this one. 1 over x minus 4 squared dx. And then here, you should do a u substitution. U equals x minus 4. This is a very simple u substitution, maybe even so simple that you feel like something's gone wrong, but it's not. It's just a very straightforward u substitution where there isn't really anything special to do with the du part. And so this, when I do the substitution, becomes just integral of 1 over u squared du. I think of this as u to the negative 2 power, of course. So this is lim integral u to the minus 2 du, and that becomes negative u to the negative 1. So t going to 4, negative u to the minus 1. And this, I replace the original variable lot of steps here. X minus 4 to the minus 1, plugging in, what were they? 1 and 4. All right. If you can manage to make it this far without messing it up, I hope I didn't mess it up. All right, and now, sorry, not 4 up there, it should be a t, because that's the whole point of this lim as t goes to 4. I meant to say t up there. So now we plug these in. We get, plugging in t, lim t goes to 4, negative t minus 4 to the minus 1, minus negative 1 minus 4 to the negative 1, right? And then what happens when I make the t go to 4? This will say 4 minus 4. You know, as usual, I just think of plugging in 4 here. 4 minus 4 to the negative 1. What is that? As usual, your chances are either 0 or does not exist. That's typically what the answers end up being. What do you think? This being a minus 1 power, I would like to write this as a fraction, as I always do. This is minus 1 over t minus 4 minus, well, plus 1 over, isn't that negative 3, I guess? Just simplifying the parentheses business. And what happens, sorry, I forgot to write my lim. Lim goes to, t goes to 4. This becomes 1 over 0, which does not exist. So that means this part of the integral diverges. I hope that's what you eventually said. It can be tempting to, right here, say 4 minus 4 is 0, and 0 to any power is 0, but that's actually not quite true because it's a minus 1 power. So this right here is, that part becomes 1 over 0, which does not exist. Diverges. I hope it's not an anticlimax. This particular one, the integral diverges. All right, and I think that'll do it for us today. Please let me know if you want to, you know, I have my usual office hours right now if you want to talk about homework problems or go over stuff for the test, or else we can talk tomorrow or Thursday also.